Today in the workshop, we're working with the versatile 555 timer IC. We'll see how the 555 works and how it can be operated in 3 different modes. We'll also build several cool projects based around the 555 timer. It's about time we did this, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be working with an integrated circuit that is actually over 50 years old. Yet despite its age, it's still one of the most useful integrated circuits ever created. Now, when the microprocessor was first created, one of the big advantages of it was this was a chip that we could use for a number of different applications, and all we had to do was program it differently and it could serve a number of different functions. Well, the 555 timer actually predates the first microprocessors, yet it has the same advantage. You can use this chip in a number of different circuits, thousands of different circuits. You probably have devices that use 555 timers in your home right now, and you may not be aware of it. And despite the fact that this just celebrated its 50th birthday last year, we are still seeing brand new devices come out that are based upon 555 timers. And as you're going to see today, sometimes it makes a more intelligent choice to use a 555 than it does to use a microprocessor. So let's go and learn a little bit more about the 555 timer and the different modes that you can run it in. This amazing integrated circuit was introduced by the Signetic Corporation in 1971. The 555 is a monolithic timing circuit. It can be used as a timer, an oscillator, or as a flip-flop. It operates from 4.5 to 16 volts. The 555 can sync or source currents of up to 200 milliamps, allowing it to directly drive LEDs and even relays. It can also directly drive TTL logic circuitry, allowing it to be used with microcontrollers. There are also CMOS low-power versions of the 555, such as the IN555, TS555, and the LMC555. The 555 is packaged in an 8-pin package. It can either be a dip or a surface mount chip. Pin 1 is the ground, Pin 2 the trigger, Pin 3 is its output, Pin 4 is the reset pin, Pin 5 is control voltage, Pin 6 is threshold, Pin 7 is the discharge pin, and Pin 8 is VCC, or the positive power supply. Internally, the 555 consists of a number of transistors, resistors, and diodes. However, it is much easier to visualize the internal operation by breaking it down into a few blocks, which include a couple of comparators, a flip-flop, an inverter, 2 transistors, and a resistive voltage divider. The 3 5K resistors wired between VCC and ground create a voltage divider. Now, there is a common rumor that the name 555 is derived from the 3 5K resistors. However, this isn't really true. One of the employees at Signetics has confirmed that 555 was just a number chosen by someone in the marketing department who thought that it was a pretty cool number. With this voltage divider, comparator 1's negative input will get 2/3 of VCC. So if VCC is 12 volts, for example, it will get 8 volts at this point. Comparator 2's positive input will get 1/3 of VCC. So with our 12-volt example, it will be getting 4 volts. The positive input to comparator 1 is connected to the threshold pin on pin 6. The negative input of comparator 2 is connected to the trigger pin on pin 2. Now, if you're not familiar with the operation of a comparator, it's just a component that compares 2 analog input voltages, and it outputs a digital signal. If the positive input to the comparator is larger than the negative input, then the output will be high. If the negative input is larger, then the output will be low. Let's take a look at comparator number 1. The positive input to this is the threshold pin on pin 6. The negative input is 2/3 of the VCC. So if the threshold is greater or equal than 2/3 of the VCC, the output of this comparator will be high. If the threshold is less than 2/3 of VCC, then the output will be low. On comparator 2, the positive input is 1/3 of VCC. The negative input is wired to the trigger pin on pin 2. If the trigger is greater than 1/3 of VCC, then the output will be low. And if the trigger is less than or equal to 1/3 of VCC, then the output of comparator 2 will be high. The two comparator outputs are inverted and are sent to an SR flip-flop. An SR flip-flop has two inputs, a set and a reset input. It also has two outputs labeled as Q and not Q. Not Q is signified with the letter Q with a line on top of it. Not Q is always the inverse of Q, so if Q is high, not Q is low, and if Q is low, not Q would be high. The set input will set the output of Q high. The reset input will set Q's output low. If both inputs are low, then there is no output change. Having both inputs high is an invalid state and will cause a questionable output on Q. In the 555 timer, only the output not Q is used. Given that logic, we can establish a truth table for the 555, showing the input to the threshold and trigger and what the output from not Q would be. Note that the not Q output is fed into an inverter before it is fed out to pin 3, so the output on pin 3 of the 555 is at the same state as the Q output of the flip-flop. Now let's take another look at the input. The control voltage input on pin 5 is connected to the comparator 1's negative. This allows modification of the threshold point, so it doesn't always have to be at 2/3 of VCC. You'll also notice two transistors in this design. The first transistor is connected to the reset pin on pin 4. It controls the power to the flip-flop. In normal condition, you would hold this pin high, thus turning the transistor on and turning on the flip-flop. If you send the reset low, it'll remove VCC from the flip-flop, effectively resetting the timer. The other transistor has its base connected to the not Q output. This transistor will therefore be off when not Q is low. The discharge pin on pin 7 is generally connected to a capacitor as well as a resistor to allow current to flow into the capacitor. If not Q is low, the capacitor will charge because the transistor will be off. If not Q is high, the transistor will turn on and the capacitor will discharge to ground through it. The value of this capacitor can be used to set timing on the 555. The 555 can be operated in three different modes. Astable mode, which produces an output regardless of the trigger input. Monostable mode, which produces an output which is initiated by a trigger and whose pulse width is determined by capacitors and resistors. And bistable mode, whose output is controlled by two triggers, one that sends it high and another one that sends it low. We'll examine these three modes in more detail in a few moments, but first let's take a look at a few 555 timers. So here we have a number of 555 timers, and it's really not that much to look at. These are just 8-pin dual inline packages, and they're very easy to work with on either a solderless breadboard or on a piece of perf board, or even for designing your own printed circuit boards. I also have these chips over here, and these are 556s, and what a 556 is it's just two 555 timers in the same package. And so this is a 14-pin package. They've got all of the pins of the 555, plus the power and ground is common to the two internal timers. So the VCC and the ground pins, there's only one set of those, and there's a dual set of everything else. So if you're ever building a project that uses two 555s, you could always use a 556, and that would work out just fine. And it might be a little easier for you to breadboard that or to build a printed circuit board around it. But otherwise, as I said, there's not really much to look at. So what I suggest we do is start building a few interesting projects with our 555 timers. So now we've seen a bit about the internal functionality of a 5-5 timer, and we've learned that it can run in 3 different modes. Technically, there is actually a 4th mode it can run in, something called a Schmitt trigger. And a Schmitt trigger is a component that can take a digital signal and clean it up. We've used Schmitt triggers before when we talked about digital logic. However, the Schmitt trigger mode is really just an extension of the bistable mode, so we're going to consider that there are only 3 modes. What I want to do now is demonstrate how you wire up the 555 timer for all 3 different modes and run a quick demonstration of each of the modes so you can see how it works. And so let's begin by looking at the Astable mode. Astable mode is also called free running or self-triggering mode. In this mode, the 555 works as a rectangular wave oscillator. The output is at 2 quasi-stable states, either high or low. In astable mode, there is no external triggering required to produce an output signal. The time that the output signal spends high and low is set by 2 resistors and a capacitor. Now here is how we would hook up astable mode on a 555 timer. The time the output spends high is determined by resistor RT1 and RT2, as well as capacitor CT. The time that the output spends low is determined by the values of resistor RT2 and CT. By changing the value of these resistors and capacitors, we can produce a rectangular output at any frequency within the range of the 555 timer. Now let's wire a 555 up in astable mode. For this experiment, we'll require a 555 timer, a 10 microfarad capacitor, 3 resistors, a 220 ohm resistor, a 1K resistor, and a 100K resistor, a 0.01 microfarad capacitor, this can also be referred to as a 10 nanofarad capacitor, a 9-volt battery, and an LED. And here's how we'll wire all of this up. In this circuit, the 220 ohm resistor is being used as a dropping resistor for the LED on the output of the 555. The timing of the output is determined by the 10K and 100K resistor, as well as the value of the 10 microfarad capacitor, so changing these values will change the output value. You might be wondering about the purpose of the 0.01 microfarad capacitor connected to pin 5, which is the control voltage. This is a common arrangement with the 555 and is used to smooth the control voltage that provides an input to comparator number 1. The whole circuit is powered by a 9-volt battery. So now let's wire this up on a breadboard and see how it works. And so here's our astable 555 timer demonstration on a solderless breadboard, and you can see my LED over here, which is the output of it, and buried within these wires down here you can see the 555 timer. Now I'm powering this with a 9-volt battery, and so I'm going to connect the batteries positive to get everything going. And you can see the results right here. The LED is flashing roughly once per second. And this basically, if we were using an Arduino, would be the equivalent of a blink sketch. So it's a good first thing to demo our 555 timer with, just as the blink sketch is the first thing we usually use with an Arduino. Now, one thing I want to point out, that as opposed to an Arduino, the 555 timer costs less than 50 cents. And with all of the other components on the board, including the LED, we've got about $1 worth of electronics over here. So this is certainly a cheaper way of flashing an LED. Plus, of course, there was no programming involved. Now, the timing of this circuit is dependent, as you've seen, on the value of a resistor and a capacitor. We're basically charging up a capacitor and discharging a capacitor. And the capacitor in this case is this one over here. It's a 10 microfarad capacitor. So let's take the power off for a second. And I've got another capacitor here. I've got a 22 microfarad one. So I'm going to pull this one out, and we'll put another one in its place. Make sure I connect that correctly. And we'll power that back up. Now I've got a 22 microfarad. And as you may have expected, the period has changed. It's about twice as long, and that makes sense because the capacitor value is about twice as big. So it's taking larger to charge up this capacitor than it did the 10 microfarad capacitor. And so that's how we can change the frequency, or in this case, the blink rate of the LED. So here we have it, our first demonstration with the 555 in Astable mode. Now let's take a look at the 555 timer in Monostable mode, which can also be called single-shot mode. In Monostable mode, the output has one stable state and one quasi-stable state. An external trigger is used to change the output from the stable state to the quasi-stable state. The output switches back to the stable state after a predetermined period. This period is set by an external resistor and capacitor. Here's how we would wire a 555 timer up in Monostable mode. We have two resistors, RT and CT. The trigger is applied to the trigger input on pin 2 and the output is on pin 3. The time that the output spends in the quasi-stable mode is determined by the value of the resistor and the capacitor. Now let's wire a 555 timer up in Monostable mode. For this experiment, we'll require a 555 timer, a momentary contact normally open push-button switch, a 10 microfarad capacitor, a 220 ohm resistor, a 10K resistor, and a 100K resistor, a 0.01 microfarad capacitor, an LED, and a 9-volt battery. Now here's how we would hook everything up. Once again, the 220 ohm resistor is taking the output on pin 3 and acting as a dropping resistor for the LED. Pin 2, which is the trigger input, has a 10K resistor that is pulling the input high. The input will remain high unless the push button is pressed, in which case it will go low, triggering the timer. The period that the output on pin 3 remains high, which is the quasi-stable state, is determined by the value of the 100K resistor and the 10 microfarad capacitor, which are both connected to pins 7 and 6. Once again, the 0.01 microfarad capacitor has been connected to pin 5, the control voltage pin, just to stabilize the voltage. And the whole circuit is powered by a 9-volt battery. So let's wire this up on a breadboard and see how it works. Now here's our monostable mode demonstration. Now remember, in monostable mode we are triggering the timer, and in this demo we're using this push button switch over here, but we could very easily be using an incoming pulse that was going low. It would do the same thing, and the output again is our LED. And so if I press the push button, the LED comes on, and then it goes off, and it comes on for a specific period of time that was determined by our timer. We'll try that again. We'll do it. Now, once again, that timing is determined by a capacitor, and once again, it's a 10 microfarad capacitor that we have over here. And so I'll repeat the experiment we did with the Astable. I'll just take the power off of this for a moment, and I'll take my 22 microfarad capacitor and put it in place of the 10. And now we'll put the power back onto that. And this sometimes activates when you first put the power on. And we'll press the switch, and as you see, the LED will stay on longer than it did the time before. So once again, that timing is being determined by the capacitor. And this is actually a very useful circuit. You could use this as the input for another device as a debouncing type of circuit. You wouldn't need to use as big a capacitor as we have over here, but one press of the push button is only going to produce one output pulse, even if there's a bit of noise on the push button. And so it's a very useful application for the 555 timer. The third mode that we can operate our 555 timer in is Bistable mode. In this mode, the 555 essentially operates as a flip-flop. Both of the output states are stable. The output will stay in one state, either high or low, until one of the triggers is applied to change the state. Now here's how we will wire a 555 timer in Bistable mode. In this diagram, the trigger 1 is applied to the trigger pin on pin 2, and trigger 2 is applied to the reset pin on pin 4. Now in this diagram, we're showing two resistors, which are simply pull-up resistors. We're also showing push buttons, although the trigger could also be a digital input from an external device. Let's wire up a 555 in bistable mode. For this experiment, we will of course require a 555 timer. We'll need two momentary contact normally open push button switches, three resistors, one 220 ohm resistor and two 10K resistors, a 0.01 microfarad capacitor, an LED, and a 9-volt battery. Now here's how we'll hook everything up in bistable mode. Once again, our 220 ohm resistor is taking the output on pin 3 and acting as a dropping resistor to drive the LED. Pin 2 is our trigger input, and it has a 10K resistor pulling it up high. Pin 4 is the reset input, and it's also being pulled up by a 10K resistor. When the push button associated with those pins is pressed, it will pull that input low, thus causing a trigger. As we did in our previous experiments, we'll be using the 0.01 microfarad capacitor on the control voltage input in order to smooth the voltage. And we'll be driving everything with a 9-volt battery. So let's wire that up and take a look at it. Now here's the third mode demonstration for our 555 timer, and this time in bistable mode. And in bistable mode, we require two triggers, one to turn it on and the other one to turn it off. And our two triggers are these two push buttons, a green one here and a red one over here. And so if I press the green button, our LED is on, and it will stay on indefinitely. It's not going to time out or anything. It's not going to turn off. The only thing that will turn it off is our second trigger, which is the red button here, and that will turn the LED off. We could try that again. We can press the green one, and what happens if we give it another trigger on the green button? We can press this as many times as we want. It's not going to affect the state of the LED. The only thing that will turn our LED off is the second trigger with the red button. And as you can probably imagine, this by itself is a pretty useful circuit. You could replace the LED with a relay and create a switch where you have a push on button and a push off button, and that by itself is quite useful. So another great application for the 555 timer. So now we've worked with the three different modes of the 555 timer, it's actually time to build some projects. And I say some projects because in most of my videos we end up by building one or maybe two projects, but today we're going to build a number of small projects, and I want to do that to illustrate the versatility of the 555 timer. And of course you can take these projects and use them as building blocks in larger projects. You could even combine them with microcontroller based projects and kind of get the best of both worlds. So without further ado, let's go and build some things with the 555 timer. Now for this 555 timer project, we're going to build a 10 LED light chaser. Our device will make use of a 555 timer as well as a 4017 decade counter. The light chaser will have a variable speed, so you can adjust the rate at which the lights chase. Now here are the parts that we're going to require to build our light chaser. We will of course need a 555 timer. You'll also need a 4017 decade counter. Now if you can't find a CD4017, you can also use a 74HC4017. If you do use the 74HC4017, remember not to go over 7 volts in our power supply. But as we're using a 6-volt battery, that should just be fine. We'll also require a 3.3 microfarad capacitor, 10 LEDs. You can use any color you want, but I would suggest keeping them all the same color. You'll need 10 220 ohm resistors, and these will be the dropping resistors for the LEDs. You'll also require a 1K resistor and a 10K trim pot. Now here's the schematic for a light chaser, and while it might appear to be a bit overwhelming, most of that is because of all the connections out to the LEDs, and I'll show you in a moment how we can simplify those connections. Before I do, let's just focus on the 555 timer. Now the 555 timer is simply being run in Astable mode, and the frequency of its output is determined by the value of the 3.3 microfarad capacitor and the position of the trim pot. So adjusting the trim pot can adjust the speed that the lights are chasing at. The output of the 555 on pin 3 is being fed into the clock input on the 4017. And the 4017 is a decade counter, meaning that it has 10 outputs, and those outputs are being fed to the LEDs. Now, in order to simplify the wiring, I've created this chart for you, and the chart shows you the function in the 4017, the actual pin number, and the LED that is connected to that pin through its dropping resistor. So this will make it a lot easier to wire up, and it's really not that difficult to wire when you have something like this. So let's wire this up and take a look at our light chaser. So here's our LED chaser wired up onto a solderless breadboard, and I want to point something out on this breadboard that may be a bit confusing if you're looking at this, because our design had two integrated circuits in it, the 555 and the 4017 decade counter, and yet it appears that I have three integrated circuits on this board, but that's not actually true. This, of course, is the 555 and the 8-pin package, and over here, buried under this mass of wires, is our 4017 decade counter. This is not an integrated circuit. This is what's called a resistor array, and all it is a series of resistors. Now, this is a 16-pin array, and it has 8 resistors in it, so it's got 220 ohm resistors, 8 of them, and there's one resistor connected from pin 1 to pin 16, another one from pin 2 to pin 15, etc., etc. And so this prevents me from having to wire up 8 independent resistors, and so it's a lot easier to wire and it's a lot simpler on board space. And of course, since I needed 10 of them, I've got 2 discrete 220 ohm resistors over here. But if you're building things like this, a resistor array is a very handy thing to have. Now, as you can see, our lights are already chasing, and the chasing effect looks pretty cool. Now I can go and take the trim pot here and adjust the speed of it. So I'll set it down really, really slow. This is about the minimum over here. So this is the minimum speed that we can chase at right now, and that's pretty slow. And I'll move it up so we can go faster. We can continue to go faster to the point where it is too fast, where it's just one blur. So this is maybe about the fastest that we'd want to put it at, and it's quite a neat effect. Now, of course, you could build an equivalent thing out of a microcontroller, but there would be a lot of wiring. You'd be using a lot of I/O ports on the microcontroller, and once again, this is a much less expensive design than a microcontroller-based design. And you could also, instead of just using LEDs on the output, this could be opto-isolators driving something bigger. You could even use solid-state switches and use full-size lights for this. And if you wanted to extend the chasing effect in that way, you could put another string of lights after that. You could just have 2 things chasing, so this first light would go and also drive an 11th light, the second one driving a 12th one, etc. There's a lot of possibilities over here as to what you could do with this very basic chaser design. Our next project is a latching switch, a push-on, push-off switch. We'll be using one push button as our input, and we'll drive an LED on the output for this demonstration. Our project uses a 9-volt battery as its power supply. Now here are the parts you're going to require to build this. We'll require a 555 timer, a 1 microfarad capacitor, 4 resistors, a 220 ohm resistor, 2 10K resistors, and a 100K resistor, a momentary contact normally open push button switch, an LED for the output, and a 9-volt battery to power everything. Now here's how we're going to hook everything up. Once again, our 220 ohm resistor is just a dropping resistor for our LED. The 2 10K resistors form a voltage divider, and the center of this voltage divider is connected to both pin 6, pin 2, and to one side of our push button switch. The other side of the push button is connected to one side of the 1 microfarad capacitor and to a 100K resistor which feeds the output of pin 3 back into the capacitor to charge it. And the whole thing is powered by a 9-volt battery. So let's hook all of this up and go and take a look at our latching switch in action. Now here's our latching switch wired up as usual on a solderless breadboard with the 555 buried in here and a few components, and here is the push button itself and the LED we're using for a demonstration. And when I push the push button, amazingly the LED lights up. And it's going to stay lit until I press the push button again, in which it turns off, which is of course the desired action. Now it's a very simple demonstration, but keep in mind this doesn't have to be an LED on the output. It can be a relay or it could be an opto isolator. You could be driving something else with it. So this is a very useful circuit, and again I'll remind you about the cost of the components. For less than $1 worth of components we built something that we could have built with a microcontroller, but was actually far easier to build with a 555 timer. In this 555 project, we're going to build a small DC motor controller. This is a unidirectional controller that has a speed control. We'll be building it using a separate motor power supply, and you can use a variety of motors and power supplies with this design. Now here are the components we're going to need to build the DC motor controller. We'll require a 555 timer and a 100K linear potentiometer. We'll also be using an IRF 520 MOSFET on the output. Now you could use a different MOSFET if you wish. We'll require a 1K resistor, 3 1N4004 or equivalent diodes, and 2 0.1 microfarad capacitors. Our circuit will be powered by a 9-volt battery. We'll be driving a small DC motor, and we'll also need a power source for our DC motor. Now here's how we'll hook up our circuit. We're using the 555 timer in an Astable mode. The frequency of the output is determined by the 0.1 microfarad capacitor tied between pin 2 and ground, and the resistor tied between pin 7 and the VCC. The pulse width is dependent upon the position of the potentiometer, with the 2 diodes modifying the pulse. The output on pin 3 is fed to the gate of our MOSFET. The MOSFET then drives our motor, and note that we have a diode across the motor that protects from any back EMF that may be generated by the motor. So let's hook this up and see how it can control our DC motor. So here's my motor controller wired up onto a solderless breadboard as usual, and you can see over here I've got my potentiometer, which is my speed control. Here is the MOSFET, the power MOSFET that is going to drive the motor, and over here is my fan, and my fan is mounted on a little piece of perf board. This is something you may have seen before. I've used it in previous videos, and it's just one of the things I use for prototyping, so I find this very easy to use whenever I'm trying to test out a motor. Now this motor runs on 6 volts, so as you can see over here I've got 4 AA batteries powering it, and I've got a 9-volt battery powering the motor driver itself. And so I'm going to just turn the speed control. And there we are at full speed, and we can reduce the speed. Bring it lower if we wish. Bring it quite low if we want to. And so we get a nice control over the speed. And of course we've seen Arduino designs that use pulse width modulation that do the same thing. But once again, I want you to bear in mind the cost of the devices over here. We're using essentially the same MOSFET that we would use with an Arduino-based design, but we're using a very inexpensive 555 timer chip. And so this is a much cheaper design than an Arduino-based design. And if all you want to do is control the speed of a DC motor, this will work great. Now you could choose a different MOSFET if you wanted to. This one has a reasonable rating on it, but you could get one that's it's rated at a higher current to drive a much bigger motor. This MOSFET also is rated for a much higher voltage, so you certainly don't need to restrict yourself to just a 6-volt motor. You could do a 12-volt or even a 24-volt one with this. And so it's quite a versatile design. So if you're looking for a PWM motor control and you don't need direction control, you might want to consider using a 555 timer instead of a microcontroller. In this 555 timer project, we're going to build a simple touch switch. Our touch switch will use 2 wires or plates, and when you touch them, the switch will be activated. In our case, we're going to drive an LED, but of course you could add a relay or opto-isolator and drive something other than an LED if you wished. To build the touch switch, you'll require a 555 timer, an LED, 2 resistors, one of them 220 ohms and the other 100 kiloohms, 2 capacitors, a 0.01 microfarad capacitor and a 0.1 microfarad capacitor, and we'll be powering this with a 6-volt battery. Now here's the wiring diagram for our touch switch. In this case, we're using the 555 in a monostable mode. And as you recall, in monostable mode, when the 555 is triggered, it will produce an output pulse of a predetermined width. That width is determined by the value of a resistor and a capacitor. In this case, the 100K resistor connected to the discharge pin on pin 7, and the 0.01 microfarad capacitor that is connected to the threshold pin on pin 6 determine the output pulse width. Now I've got it designed so that when you touch the switch, where you touch the 2 plates, the LED will only come on for about a second. But you can change that period of time by adjusting that resistor and that capacitor. The other resistor, the 220 ohm resistor, is of course just a dropping resistor for our LED. So let's wire up our touch switch and take a look at it in action. So here's my touch switch wired up on a solderless breadboard, and for touch switch sensors, all I used was a couple of pieces of wire. You can see them back over here if you look carefully. They're on the breadboard, and when I touch these together, the LED should light up. So let's just do that. And the LED does indeed light up when I touch this. And so another very simple 555 demonstration. Now remember, because this is a timer, the value of a capacitor and resistor are determining how long the LED would be on. So you could change those values and actually keep the LED on for a long time, even a couple of minutes if you wanted to. And that might be a useful type of arrangement to have, something that you touch that just put a light on for a predetermined period of time. There's a lot of possibilities here. And of course, you don't need to use just an LED on the output as with all of our demonstrations over here. And so another good use for a 555 timer. This 555 timer project can be used to test the operation of servo motors. It works with 6-volt servo motors, which are the common hobby type that we normally use in our projects. It has 2 buttons, one to send the servo in forward and another to send it in reverse. To build this project, we'll require a 555 timer, 2 momentary contact normally open push button switches. We'll need 5 resistors, a 220 ohm resistor, 2 10K resistors, a 33K resistor, and a 68K resistor. We'll also require a 0.1 microfarad capacitor. I'm using a 2N2222 transistor in this design, but you can use any equivalent NPN transistor. And we'll also be powering everything with a 6-volt battery. Now here's how we're hooking up the circuit. The 555 in this mode is acting as an astable multivibrator whose frequency is determined by the capacitor tied to pin 2 and the resistor tied to pin 7. The pulse width is determined by the 2 different resistors tied to the push button switch, and this is why one of them will send the servo forward and the other will send it backwards. The output of the 555 is connected to the base of our transistor through a resistor because transistors are current driven. So let's hook this up and see if it'll move our servo motor. And so here's my servo motor tester circuit, and as always, I've got it on a solderless breadboard. I've got my 2 push buttons, which should control the direction the servo is going, and naturally I have a servo motor connected as well, and this is being powered by a 6-volt power source, which is 4 AA batteries in this particular case. And so pressing this button should move it in one direction, and pressing this one moves it in the other direction. And it seems to work very well. One thing I notice actually, compared to some Arduino circuits, is there's no chattering on the servo when it's sitting there stationary. It's just sitting there perfectly stationary doing nothing, which is actually great. And that's because, of course, it's not actually getting a signal right now. And so it does have an advantage over that kind of a system. And you could use something like this to actually drive a servo motor, not just test a servo motor, but of course you would need to experiment a bit with the value of resistors that were attached to the switch or whatever it was that you were using in order to drive the motor. But again, another great use for a 555 timer. So this brings us to the end of our look at the 555 timer, but it's by no means the end of the number of applications that this amazing little device has. In fact, quite possibly we'll be using these devices 50 years from now. Now, if you want to get a bit more information about the 555, or if you'd like the hookup diagrams for all the little projects we built, just head over to the DronebotWorkshop.com website, where you will find an article that accompanies this video, and there's a link below the video to that article. And while you're on the website, if you haven't yet, please sign up for my newsletter. It's not a spam letter by any means, of course, and it's not a sales letter. It's just my way of letting you know what goes on here in the workshop, and all I need from you is your email address. And if you want to discuss the 555, or if you want to perhaps show off some of the projects that you may have built with this amazing little timer, a great place to do that is on the DroneBot Workshop forum, where you'll find a number of other electronic enthusiasts who not only work with 555 timers, but with microcontrollers and all sorts of great things. And the forum is free to join. There's a link below the video to joining the forum. And of course, if you haven't subscribed to the YouTube channel, please do. I love getting new subscribers, and I'd be honored if you would subscribe. All you need to do is hit the subscribe button and also click on that little bell notification. And assuming that you've enabled notifications on your YouTube, then you'll get notified every time that I make a new video. So until we meet the next time, please take good care of yourself. Of course, please stay safe, and I will see you again very soon here in the DroneBot Workshop. Goodbye for now.